My name is Daniel Cremers. It's a pleasure for me to be here once again. It's always a great place to be. Initially, I was going to talk more about machine learning, about neural networks, etc. But as we heard earlier this morning in Guillermo's talk, the machine learning field is very active, and there is a chance that whatever I tell you about machine learning, there is 5 other papers who do essentially the same thing, and then I didn't want to bore you with things that everyone else is also doing. And in addition, I saw that I'm speaking in the same block as Marco Couturi, who is speaking about optimal transport right after me. And so I thought this may be a good opportunity to tell you a little bit about a topic that is very close to optimal transport, yet different. I'll not actually speak about optimal transport myself. I'll not even mention where the differences are. I'll just talk about this topic that is very dear to my heart. It's a topic called shape analysis. So and this is work, I should say, that was predominantly done by 4 of my current and former students. The topic is something that you're all familiar with. We live in a 3D world, and we have 3D objects all around us. And one of the challenges is to devise mathematical tools to analyze 3D shape. For example, given 2 3D shapes, you may want to be interested in what is their similarity. And as a human, we see 3D objects and we immediately perceive similarities, but it's far from trivial to formalize this on a mathematical level and also on a computational level. For example, one of the things to note is that 3D similarity is closely coupled to the notion of correspondence. You would say these 2 objects are similar because you can have a transformation that maps one paw into the other, the ears into the ears, the muzzle into the muzzle. And so clearly, understanding 3D shape, measuring similarity is coupled to the problem of correspondence estimating. Matching shapes. And another thing we may be interested in, I'll also be speaking about that, is interpolating 3D shapes. Given 2 3D shapes, can I create a whole family of intermediate shapes? And among all conceivable families of intermediate shapes, which one might be the most suitable one? But before I go into that, let me tell you why I'm particularly interested in it. Over the years in my research team, my field is the field of computer vision. We've developed algorithms and methods to reconstruct the 3D world from images. For example, you can take a collection of photographs, typically 20 or 30 photographs, and you can devise algorithms that reconstruct the 3D objects seen in these photographs at a fairly good level of detail and precision, where you can see the hammer, the sword, everything, just captured from standard cameras. Once you move into other cameras, for example, depth sensing cameras, you can even develop techniques that create color-dense 3D models, as you see it on the screen here, in real time. Just turn the person on a chair in front of a depth sensing and RGBD camera, something like a Microsoft Kinect or Asus or whatever, and then you can immediately print them. So we can, at this point, we can copy the world in real time at a great deal of ease, and then obviously this project became super popular, and so then the president of TU Munich contacted me and wanted his 3D model, and then and the prime minister of Bavaria also wanted to be scanned. Everyone wanted to be scanned, and then I felt a little awkward, moving the chair around with the president sitting. So we developed a more standalone version where we have a robot arm. You just click a button, and then this arm with 3 Kinect cameras or Asus cameras pans around, and again in real time creates that 3D model here of the TU Munich president. So this is a full model. We can print it, and he was quite happy. He has him standing on his piano. And of course, the prime minister, once we print him out, we need to print him twice the size, and I'm sure where that's heading. But what I'm showing you is we can scan the world around us. We can create 3D shapes very easily of things around us. For example, we can even go further and reconstruct actions over time. We can film actions such as this rope jumping girl, where in this case with 16 synchronized cameras. When I say we can film it, this was actually not filmed in Germany, but in France. This is footage that was recorded in Edmond Boyer's lab in Grenoble. But we can take this data that they provided online and we can reconstruct the whole action, as you can see, at a level of detail and precision where the entire rope of the rope jumping girl is recovered in the reconstruction. And so, as you can see, we can reconstruct the world around us. And that raises once more the question, how do we analyze 3D shape? In this talk, I will focus on elastic shape matching and computing correspondence and interpolating shapes, but there's underlying always the notion of shape similarity. Because ultimately, when you match two shapes, you can use the overall matching cost as a metric between the shapes, on the space of shapes. I have three parts here. The first part I will talk about planar shape matching, because in planar shapes the world is a little bit easier, and I must admit significantly easier. When my first PhD student that I ever recruited in 2005, I told him to just extend the planar shape matching algorithms to 3D shapes, and I thought this would be a project of a few months. And here I stand, more than 10 years later, and we've advanced this, but it turns out it was significantly more difficult than I would have anticipated, and I'll come to why that is in a second. And then I'll talk about, this is a very recent work where we talk about not just matching and correspondence estimation, but also interpolation and extrapolation of shape. 2D shape matching is a very classical problem. So you're given two shapes. I don't know if you can see it well. These are the two hand shapes, a blue one and a red one up here. And they are similar, but the red shape misses one finger. And so one of the things that you may want to do is in measuring shape similarity and computing correspondence, you want to account for missing parts. You want to account for the fact that something may have shrunk. And so the transformations that you're looking for are not necessarily isometries. In particular, isometric shape matching is a big area in the shape matching area. We don't want to have isometries because we want to capture this shrinking and stretching. And so we want some form of elastic shape matching, and this has been worked on by many, many people over the years. These are works from the 90s and later. There's more recent works as well, so this is a never-ending kind of research topic. One of the things that was figured out very early on already, for example, in this really nice paper of Metz in '91, is that you can phrase that shape matching problem as a shortest path problem. And the way you can see that is you essentially identify, maybe by hand, an initial correspondence, say this point matches to this point, and then you can basically compute the overall matching as a shortest path, where you can see these are the points along one shape, these the points along the other, and what you have here in the graph, in this 2D space, is, for example, the local similarity, the local curvature similarity of the two shapes. And then you can say, find a correspondence between points on one shape and points on the other, such that the local curvatures are as similar as possible. So positively curved points match to positively curved points, negatively to negatively, etc. And then computing the overall best correspondence in this fashion can be done by computing the shortest path from this point here to this point there. That's really nice. Once you don't know the initial correspondence, it's a little bit more difficult, but actually still solvable in polynomial time. So then you have matchings. You assume you have the curvature for your two shapes. Let's call them C1, C2. They're parameterized on the circle. And so we have the curvatures for these, and then what we want to compute is a reparametrization, essentially, of these two shapes, such that the curvature of one and the curvature of the other are as similar as possible in this least square sense. And so we try to optimize over the orientation-preserving diffeomorphisms here. And this is the problem we want to solve. And you know, for me, what is helpful is to visualize a little bit what is, kind of geometrically speaking, the problem that we're solving here. And you can see it as finding a shortest cyclic path on a torus, where you can see this circle corresponds to the points on the blue hand, for example. This circle corresponds to the points on the red hand. And now you can easily verify that any matching elastic matching of the blue shape to the red one, preserving the orientation, corresponds to a cyclic path on this torus. If we know the initial point, then we know it goes through some point here. If we don't, then it's some cyclic path starting somewhere here and looping around each of these circles once. And so the aim is to compute shortest cyclic paths on a torus. This in itself is polynomial time solvable. For example, a naive solution would be to just, so basically, for those who haven't understood the concept yet, if you take one edge along this path, it puts in correspondence an edge on the red shape with an edge on the blue shape. That's essentially the idea. And any correspondence can be discretized on this discrete grid as the shortest path on this cyclic, on this torus. But as I said, we don't know the initial correspondence, so we're not sure that the path necessarily goes through here. If we knew it goes through here, then it's just a simple Dijkstra algorithm that you can run to find this path. The brute force solution that was actually done by many researchers over the years is to try all possible initial correspondences every time run another shortest path algorithm. Unfortunately, I mean, this works, this can be done, but it turns out this is not the most efficient way to do it. And what we proposed in 2007 is basically you cut things open, and then the aim is not to compute the shortest path from this node here to this node down here, but the shortest path from all nodes here to their corresponding partner down there, and among those, the shortest one. And what we showed, I don't want to go too much into detail, that you can devise a branch and bound strategy. This was also introduced by Mess already in the 1990s, that you recursively subdivide this domain, and then you compute shortest paths from, say, for example, these three nodes to their respective partners down here. And what we exploit then is, in this algorithm, is notions of shortest paths, for example, that shortest paths never cross each other. So that means if this shortest path, say, goes down here, and this one goes down here, then we know all shortest passes from this interval to the corresponding interval have to go through this bottleneck. So we can then rephrase it and just find a shortest path that goes through this point. And this way we can very efficiently prune the whole area and recursively subdivide it. I won't go too much into detail, but one of the things we found is that we can actually compute the worst case complexity of this algorithm. If n is the number of nodes on one planar shape, then we have a complexity of n squared log n to compute this. Whereas if you try each initial point, you would have n cubed as a runtime. And in fact, here's a comparison to alternative algorithms that people have proposed in the literature. This is the n cubed complexity, exactly n cubed here, and this is the algorithm that we propose. So here, sorry, this is the number of points on the shape, and here's the runtime in sequence. And this makes a difference if you have very high resolution shapes with thousands of nodes, then you know you don't want to do n-cubed algorithms, obviously. So this was nice, and so I thought, well, the planar shape matching is polynomial time solvable, should be a piece of cake to extend that to surface matching. Given two surfaces, compute the correspondence in a similar fashion. You know, it's just one more dimension on each shape. How much can that, you know, destroy the problem? Well, I set my student on this topic, and I was admittedly very naive. Sometimes I think it's good to be naive, otherwise you never tackle certain problems. So I was hoping he would solve it in half a year. He actually spent a full year studying the problem, and then he came back and proved to me that this problem is not in the same polynomial time solvable category. But before I go into that, some related work. This is just a little bit of related work here on shape matching and shape similarity. One work that inspired us here is these works by Martin Rumpf and his students over the years, who used the so-called thin shell model to measure shape similarity. But there's also the Gromov-Hausdorff approach by Mimoli and Sapiro that you can use for shape analysis. Then there's lots of feature descriptors like the heat kernel or the wave kernel signature that people develop for analyzing 3D shapes. For those who don't work in this area, these descriptors are much like SIFT, not for images but for shapes, right? To kind of measure local similarity. There's frameworks for diffeomorphic matching, combinatorial algorithms that people propose to match points and point clouds. The most similar one, as I said, is this one, the works of Martin Rumpf and collaborators. The main difference of what I'm presenting now is that they, in fact, minimized the cost function locally. And these are the two alternative strategies. If you set up a cost function for shape similarity, say on the space of diffeomorphisms that transform shapes into each other, typically these cost functions are highly non-convex. And then you can start with a suitable initialization and do local gradient descent or something like that. Or you can try to rephrase it and convexify the problem, and this is what I'll talk about now. So here's the two shapes. Let's give them names. One is called X, one is called Y. And what we're trying to compute is a matching that assigns to each point on X some point on Y. And moreover, obviously, we want to cover all points on Y. It's not obvious, depends on what problem you're solving, but here I assume that every point on X has a partner in Y and vice versa. There may be shrinking and stretching, but there is a correspondence. You can do that we want a symmetric correspondence, so as you know, if we want to interpret that as a measure of similarity, as a metric on the space of shapes, we need symmetry, meaning if you exchange X and Y, you should have the same cost. And we do that very simply by assigning a cost to each diffeomorphism, and then the inverse, we also add to the cost, and that way symmetrize it. And we try to minimize that cost on the space of orientation-preserving diffeomorphisms. Here is the specific cost we use, as I said, inspired by the works of Martin Rumpf and collaborators. It's the so-called thin shell energy that was developed in the elasticity theory in the 60s. There's many papers on this. The cost has two components. It looks a little bit complicated if you don't work in this area, possibly, but it's actually not difficult. There are two components. One is the so-called membrane cost, and one is a bending cost. The idea is that you treat shapes as thin shells, and there's essentially two things you can do to a thin shell. One is you can bend it, and that creates bending cost. And not surprisingly, the bending cost is proportional to the quadratic difference between the curvatures there. So the curvature of one shape and the other, if it deviates, then basically it's because I created some bending. And then in addition, you have a membrane cost. This is, accounts for the other deformation you can do, is you can stretch or shrink one shape compared to the other, and that creates a membrane cost which is proportional to, there's two terms parameterized with a weight mu. One is the trace of this Lagrangian strain tensor. So, sorry, E is not this energy, it's the Lagrangian strain tensor. And here the trace of the squared Lagrangian strain tensor. Again, I don't want to go too much into the cost here, but what is important to note is that this is not convex. So if you consider that as a function of the diffeomorphism phi, it's highly non-convex. And so the question is, can we nevertheless compute optimal solutions to such problems? Why did I think this should be possible? Well, because in the planar shape matching we had a polynomial time solution. polynomial in the number of discretizations, in the number of edges of the shape. Here, in a similar fashion, we can triangulate the two shapes and find something that is hopefully polynomial in the number of triangles. Hopefully. That was my ambition. I should say up front, we did not manage to do that. We failed. Nevertheless, I'll show you how far we got. So the idea is, inspired by this planar matching, is there a way, does the shortest path solution generalize to surface matching? Simple question, and the answer is no. Because here we reparameterize the circle, so we find a mapping from the circle to the corresponding points on the two shapes, S1 cross S1. This is exactly the shortest path on the torus, right here. And if we generalize that to surfaces, so now instead of having a planar curve for one shape, planar curve for the other, I have an S1 surface for one shape, a spherical surface for one shape, spherical for the other. So basically we have two spheres rather than two circles. And that means what we are computing, the correspondence, is a mapping from S2 to S2 cross S2. And what does that mean? It means the problem we're solving is not of dimension 1. It's not a shortest path problem. But it's also not codimension 1. It's dimension 2 and codimension 2. And that means you cannot phrase it as a shortest path problem. And also you cannot phrase it as a, say, minimum cut problem in a graph. Like a minimum ST cut problem, another polynomial time solvable problem. So in some sense, this dimension 2, codimension 2 doesn't fall in any polynomial time solvable category that I'm familiar with. If you have ideas, then I'd be very open to hear them, but we couldn't find a way to make this polynomial time solvable. But, so at that point I gave up. I said, well, too bad, so find a different topic for your PhD thesis if this doesn't work. My student, fortunately, and this happens with some of my best students, despite me giving up, he did not give up. I always say, if your supervisor tells you to give up, maybe you should not. So he continued. He looked at this shortest path problem and found a reinterpretation of it that is actually well known in the optimization literature. Namely, you can phrase it as an integer linear program. And this is where the similarities to the optimal transport emerge, which, as you know, can also be phrased in the Monge-Kantorovich formulation as an integer linear program. And so here's how it is. Basically, I label all the edges of this torus with binary labels. 1 if that edge is part of my shortest path, and 0 if it's not part of the shortest path. And then the overall cost of the shortest path is obviously linear. Basically, you have a cost for each edge, yi, that tells you how good is the local matching of this edge of shape 1 to this edge of shape 2. And then you have an assignment variable which takes binary values. If that edge is part of the path, you aggregate that cost, otherwise you don't. In addition, in the shortest path formulation, you have these linear constraints. The second linear constraint basically says if I project this yellow solution onto shape 1, I have to basically match each of these edges once. So each of these edges in shape X is accounted for. Similarly, each edge in shape Y is also accounted for. So as I said, everything gets matched somewhere. This is the requirement that I have. I don't want an empty set. I want that every structure in either shape has some corresponding structure in the other. In addition, we have a constraint, and this is the one constraint that you don't have in the optimal transport formulation. It's a continuity constraint. This is a so-called boundary operator for the planar shape matching. It basically means for each vertex on this graph, the number of incoming and outgoing edges must be the same. So if there is a path leading into this edge, into this vertex, there must be a path going out as well. This is what this boundary operator assures, and it's just the difference between incoming and outgoing edges must be 0. And this is a linear constraint. It assures connectivity of this shortest path, and this is typically what you don't have in optimal transport formulations, where you don't need structures to remain connected. You can basically, in this earth mover's distance, ship some earth here, some earth there, and it can disconnect. Here we want to assure connectivity, that's why we have this additional constraint, and that turns out is the constraint that makes the problem NP-hard. And that means there is no polynomial time solution to this integer linear program, at least none that I'm aware of. Nevertheless, it can be solved approximately. And so how, and this can be done, so for, one should say for planar shapes, this is polynomial time solvable because the constraint matrix here turns out to be totally unimodular, and then the integer linear program admits integer solutions that you can compute efficiently. In the surface matching, it turns out we can phrase it exactly as this problem, except the constraint matrix is no longer totally unimodular. And that's where the polynomial time solvability kind of breaks down. How does that look for surface matching? As I said, you discretize the two shapes by triangles, several thousand triangles on either shape. And then for each triangle, much like the edges in the planar shapes, for the triangles we ask, are these two triangles in correspondence, yes or no? Very simple question, binary variable that we associate with each pair of triangles on either shape. And the variable is 1 if they are in correspondence and 0 if they're not. By the way, to be very specific, each triangle on one shape can match to each triangle on the other shape in 3 different ways, right? Obviously, provided we preserve the orientation, and this is one of the things we can do. We can assure that triangles only match if they have the same outer normal. Something that you cannot assure if you tackle the surface matching problem as a point cloud matching, then you have no notion of orientation. With triangulations, you have a notion of outer normals, and so there are 3 possible binary variables representing a matching of these 2 triangles. Similarly, I said we want to allow for stretching and shrinking. How do we do that here? Well, we allow that any triangle here can collapse to an edge there, and we represent that, local property by a binary variable associated with each triangle and each edge on the other shape. Again, binary variables that say this triangle collapses to this edge, and again there is multiple ways to create such a collapse. In fact, this vertex here can either move up there or it can move down there. And in both cases we have a collapse, but these are 2 different binary variables that we introduce to account for these transformations. And so that way we can boil down the entire surface matching to local matching solutions, local matching costs as well. And overall, that means we introduce tons of binary variables to account for these basic correspondences, as we call them. We have a respective assignment cost, and that assignment cost can capture the local kind of thin shell cost. How much stretching do I have to do to transform that triangle into this triangle? How much bending do I have to do to match these local structures here? And that cost is aggregated in yi for each pair of triangles. And then the aim is simply, the matching can be phrased as finding the best binary configuration of all these variables to solve this integer linear program, where again we have the linear assignment cost and then these linear constraints that preserve connectivity. So for example, this boundary operator in this case of surface matching is a little bit more complicated, but it essentially says if 2 triangles match, then the adjacent triangle should match to something adjacent as well. As I said, unfortunately, this is an NP-hard optimization problem, but what we can do is we can drop the binary constraint, so allow real values for all these pairs of triangles, and then we can solve that convex problem and sequentially binarize. There's different strategies to do that, to basically solve the respective linear programs and then iteratively binarize. The way you can see that is, what we do is we basically allow each triangle a pair of triangles has a real variable, which can be, loosely speaking, we say how likely are these two triangles in correspondence, and then we can solve the problem, get a real valued solution, and then look at which of these variables is most close to 1. That means which pair of triangles is most certain that they're in correspondence. Once we fix that to 1, basically it's a little bit like matching the two shapes and pinning them together at one point with a needle and saying, here I impose they should correspond, and then we can solve the residual problem again and iterate that process. Typically it takes some 10 iterations to converge. And that way we get a solution that is obviously not the provably optimal assignment, but it's a solution that does not depend on initialization, and it's not a local minimum as in the gradient descent strategy. And so what we showed is that we can match shapes that typically consist of several thousand triangles. As you see here, it's a bit hard to visualize this correspondence. So what we did at the time is we said, let's interpolate the two shapes along the computed correspondence. And this is what you see here. Hopefully. Yes. So here we took the cat and the lion, and we basically morph them into each other along the computed correspondence. And the fact that these intermediate shapes look plausible, that the ears grow and shrink, shows you that the correspondence is fairly good. One should be careful, though, with this way of interpolating shapes, because it's just a way to visualize the correspondence. For example, if I have two humans, one with arms down, one with arms up, even if I compute the perfect correspondence and then linearly interpolate, then halfway through there is no arm, right? So I'm not saying that this is how you should interpolate shapes. I'll come back to shape interpolation later. We just use this for visualization purposes. Next, we wanted to show that it can also work for shrinking and stretching. So this may be a bit brutal example of a person that's missing a head and missing a leg, and what you see is, what's important, again, this interpolation is just a plain linear interpolation between the corresponding structures, but what's important is we find a correspondence where all these patches that you see here are hardly affected. So the correspondence seems to be quite accurate on that level. It really grows the head and the leg without really affecting any of the remaining structures. Now you can compare to many things in computer vision. They always want you to compare to everything and it's a bit tedious. What we compare to here is a work of the Bronstein brothers. They proposed a framework based on the Gromov-Hausdorff metric, and it's a point-based matching. So one of the things that, as I said, you don't have when you treat shapes as point clouds, you don't have a notion of orientation. And so one of the things we found is that in the quantitative evaluation on a data set of 30 shapes, we found that very frequently it inverts the orientation. And sometimes it inverts it partially. So here, for example, you see the left foot of this lady is matched to the right foot of this lady. That in itself I would find okay, but at the same time the left arm is actually matched to the left arm here. So somehow halfway in the waist it inverts the orientation in the matching, because there is no notion of surface orientation. It cannot assure that the orientation is preserved in the matching, whereas our approach can assure it, and as a result you get a significantly smaller mean geodesic error in the correspondence. And then you can, once you have done that, you can answer all sorts of very important questions. One question that I think most people have wondered about at some stage of their life is, what is the difference between men and women? And so we can now compute it. We can take a man and a woman and compute the correspondence and measure the similarity or difference. I don't remember what number came out, but yeah, it's probably not very helpful in answering that question. But still you see that we can account for significant shape differences with respect, in terms of this stretching and shrinking. As I said, this linear interpolation, you saw it also in the last example, is not a good way to really interpolate 3D shapes. And so that gets me to my last part in this presentation. How can we, given two 3D shapes, say the two gray dogs at each end, how can we interpolate these shapes? This is work, I should say, by Marvin and Zora, fairly recent results. So what we want to compute is a family of intermediate shapes that somehow interpolate between this dog and that dog. And obviously there's infinitely many possible intermediate shapes, so the question is, how do we formalize the problem? Which interpolation should we go for? And what Marvin and Zora suggested is to cast this as an initial value problem, where we compute a 3D displacement vector field. We call it V. And then basically we have to solve this initial value problem. So we have a set of points representing one shape, and then for each point on one shape, at time 0, we should be on one shape, and at time 1, we should be on the other shape, and in between we have this initial value problem. So the velocity vector field tells us how things get transformed, interpolated in 3D space. And now, among all these interpolating vector fields, we choose one that preserves the volume. This is very important because one of the things you know, if you have two 3D shapes, you know, they may be articulated, they may be deformed, but they should have the same volume. This is our assumption. And there is a very elegant way to constrain that the volume should be preserved. Namely, we fix that the vector field V that we're looking for should have divergence 0. Because if the vector field has divergence 0, then it is locally volume preserving. That means for any volume in that space, omega, so any area, the volume is preserved over time. This is a property of divergence-free vector fields. And so this is not only the overall volume of the two shapes that we're given, but it's also the local volume. So if I move my arm, then even locally each finger should preserve the same volume in the whole family of intermediate shapes. And so we're looking for vector fields. Here's a visualization in 2D. Let's say you have two bats, the red and the blue one. You want a displacement or a deformation of the blue bat into the red one such that the volume is preserved over time. And once you assure that the vector field is divergence-free, meaning it has no sources or sinks, then that obviously preserves the volume. That's the first idea, volume preserving shape matching by imposing divergence-free vector fields. Another obvious fact is the space of divergence-free vector fields is a linear space. So this is very nice in terms of optimization. We can constrain to that linear subspace of divergence-free vector fields. Furthermore, there's an even more nice property of divergence-free vector fields. A vector field is divergence-free if and only if it can be written as the curl of some potential function. And so rather than searching for a vector field, we can go ahead, at least for sufficiently smooth vector fields, one should say. And we're assuming that we have C infinity vector fields here. That means rather than searching for a suitable vector field, we can search for a suitable potential field. And then the vector field given by the rotation of this potential field is by construction divergence-free. Now, how do we search for suitable potential fields? What we do is we choose this Laplace-Beltrami eigenspace as a basis. This is a rather natural basis when you talk about 3D shapes. So these are the eigenfunctions phi k to the Laplace-Beltrami operator. And in fact, in our setting with suitable boundary conditions, you can actually write down these eigenfunctions explicitly. This is what they are. And so you can then represent your vector field V as a linear combination of these eigenfunctions Vk with coefficients alpha k. And these basis functions are exactly these here, with the 3 components here. And these are the eigenfunctions of the Laplace-Beltrami operator. And the union of all these is our set of basis functions. And this is a very, I would say, natural representation for your vector field of divergence-free vector fields. It also offers a natural coarse-to-fine representation, and so we can even impose like a Gaussian distribution if we want on these coefficients, where the lambda k's are related to the eigenvalues of the Laplace-Beltrami eigenfunctions. And so here's examples of what these vector fields, these base vector fields look like. You know, here's a simple rotation, basically, I think is the first component. And then you have respectively higher order components. And so if we constrain the number of eigenfunctions that we use here by k, and we impose a Gaussian prior, it basically creates a low-pass kind of filtering, meaning we favor smooth vector fields, and we suppress kind of the more high-frequency vector fields. What's important here, and this is very different to the shape matching we did before, these vector fields are defined in continuous space, and so we can decouple the resolution of our shape, the triangulation of the shape. We can preserve thousands of triangles and still represent the displacement of that 3D structure in a very coarse manner if we want. So the deformation is modeled in this kind of natural coarse-to-fine representation. I don't want to go too much into detail. What we then do is, given 2 3D shapes, we compute the suitable representation of these divergence-free vector fields by an EM algorithm that transforms one, that solves this initial value problem and transforms one shape into the other. And with that, we can create families of interpolating shapes. So for example, here, if we take this example of these 2 shapes, we can create a whole, as you can see, family of intermediate shapes. And the nice thing is this works extremely efficiently even on very high resolution shapes, because the deformation is modeled in a resolution that is independent of the shape resolution. And so you can transform and morph and interpolate very realistic high-resolution 3D shapes, as you see here. Sometimes it's better visualized in video. So what we have, as always, we have 2 shapes, one here with the arm up, one with the arm down, and all the intermediate shapes you see are simulated by our algorithm. And for me, this is, I think, a very important aspect of 3D shape understanding. If I can start to interpolate 3D shapes and synthesize, virtual shapes that look extremely plausible. So we can take the armadillo in 2 configurations again and create a whole family of intermediate armadillos that looks extremely realistic, as you can see. Well, realistic if you've ever seen an armadillo jump, That's how far the realism goes. But I think this is, and obviously once you are in the process of interpolating shapes, we have that vector field, we can just keep going, and we can extrapolate shapes as well. So given 2 shapes like these gray dogs here, so these are our input shapes, we can not only interpolate a family of intermediate shapes, a continuous family of intermediate shapes, but we can also extrapolate. So you see this dog looks forward, this dog looks a bit to the right, and the extrapolated one looks even more to the right, so it turns the head even further. Sorry, I don't have videos for the extrapolation. I have to ask Marvin to create videos. This is quite recent work, so we haven't really done all the promotion materials, if you want to call it this way. Here again, this turquoise is an interpolated shape, and the purple is extrapolated. So we can create interpolations and extrapolations. And obviously, the one problem that we solve implicitly along the way with interpolating 2 shapes, we solve the correspondence problem, because we can simply check where does this point on one shape end up on the other shape. And so we can quantify the precision in terms of correspondence, although we didn't really set out to solve the correspondence problem, but the interpolation problem. We can still look at how well does this approach do in terms of compares them to existing solutions. And what we found is here's the geodesic error in percentage of diameter, here's the percentage of correspondence. You want to be up in the left corner here, and you see we're not outperforming everyone. Our curve is the red one here, but nearly everyone. We're not far from the best performing methods on correspondence, although this is really more a shape interpolation approach. So we say you can jointly solve interpolation and correspondence by this volume preserving deformations. I'm running out of time, so to summarize, I talked about how to phrase shape correspondence estimation as an integer linear program, and I showed that this can be used to do planar shape matching where solutions are polynomial time, and then also surface matching. One thing I didn't mention is we also recently did a work on 2D to 3D matching where you're given one 3D shape and a 2D silhouette, and you want to compute where is the 2D silhouette on the 3D shape. It's also polynomial time solvable. And lastly, I talked about not just correspondence estimation, but shape interpolation and extrapolation, and how to use divergence-free vector fields in order to perform volume-preserving interpolation. Thank you.
Is there questions?
Thanks for the great talk. My question is probably out of my ignorance of this subject, but is this problem of 3D shape interpolation and extrapolation, is this already solved in 2D, or does your model generalize trivially to the 2D case?
Well, it's not solved in the sense there exist lots of algorithms to do 2D shape interpolation. This approach trivially extends to 2D. So typically, once you have a solution for a higher dimensional problem, in my experience, it's fairly easy to make it work in lower dimensions. The converse is not so easy, as I mentioned, not always. So this is, I find interesting, some approaches easily extend, are independent of dimension. The last approach, for example, doesn't really care about dimension of the problem. So this would extend to any dimension. But other approaches, in particular with respect to polynomial time solvability, it's not trivial to change the dimension. Like shortest paths are polynomial time solvable, minimal surfaces in any dimension, generally not.
At the first, you talked about multi-view reconstruction from 2D,
yes,
many 2Ds to 3D, and then you talked about shape, 3D shape interpolation. A question is, can we combine the two? So for doing 3D shape
yes,
interpolation, can we go in 2D and come back?
Yes. So this is what we're working on right now, is to so there's a lot more I could talk about, but one of the things we're working on is reconstructing actions over time such that you have a consistent interpolation. And consistent can mean many things. For example, one thing we just did very recently is we showed that you can reconstruct an action over time such that it's consistent with physics, with actual, finite element simulations of deformable objects. And so then you're not inferring the surface of the 3D structure, but you're inferring the underlying physics of elasticity, of masses, momenta, etc., etc. And I think this is quite a fascinating direction of research, because I think we as humans capture the physics of the world around us much more. Okay. There's one.
Okay. Quick question then.
I wanted to say, first of all, that in pure math, in differential topology, there's something called the Smale conjecture. So Smale proved something about contractibility of the space of embedded circles in R2 in the early 60s, and he conjectured the same thing should be true for surfaces in R3, which is what you're talking about. And it turned out to be an extremely hard problem. So there's a paper by Hatcher in the 90s that still nobody understands, where he claims to have solved it, but it's published. And there's more recent work using curvature flow that hasn't quite solved it, but it's maybe on the way. But I just wonder if you've had any interaction. And actually, in higher dimensions, there's obstructions. It's not contractible. So if you were looking at data in 3 or 4-dimensional manifolds, there would be obstructions from what's called the theory of pseudo-isotopies. But anyways, I just wonder if you've had any interaction, because there's... to a pure mathematician, it's not surprising, but the surfaces in R3 is much, much harder. There's also work on the NP completeness by some people in UC Davis, I think, related to knots also, deformation of knots.
So I'd be very happy to hear more about what you... I'm familiar with some of the works of Smail and others, but I'd be very keen to... I haven't seen the connections to what we are doing, but I'd be very keen to discuss maybe after the presentations. Maybe if I may use that opportunity, since I have your attention, we are desperately looking for postdocs in you know, I know everyone is looking for them, but you know, in particular. Munich is a wonderful place, and if you don't know what to do in the future, please reach out to us. We really need you. Thank you.
Okay, thank you.